And it's Wednesday, and it's the 7th, and we're doing parametric equations. Yay! Okay, so let's say, are you with me, guys? Okay, let's say, let's graph something here. Let's say here's a y-axis, here's an x-axis, and let's label stuff. Okay, and let's say you have a path like this. All right, so this is a path of a particle in space. All right. What if I want to know the length of this path, what I'm going to call arc length from here to here? Remember arc length? How did we figure that out? We have to review that first today. Do you remember the formula? No? S equals, yeah? Stuff. An integral of stuff. All right, so let's derive it from scratch. Okay, let's do a Riemann argument. Let's say I take a little microscopic slice of the path. Pretend it's microscopic. And I blow it up. It might look a little bit like this. Remember local linearization? If you have a differentiable and curve, which implies continuity, if you blow it up enough, it's going to look almost like a straight line, right? So let's say I blow it up, and that little section looks like this. Let's say this is the arc, the path that the particle is taking, okay? I'm going to call that ds or dl for arc length, whatever you want to call it. This piece, I'll call it dx. It's infinitesimally small. And this piece I'm going to call dy. And there's a right angle here, a right triangle. So what's the relationship between these three quantities? Right, so Pythagoras, right. Dx squared plus dy squared equals dl squared. Okay, now remember, we solved for L. Didn't we? Do you remember how we did this stuff? If you divide everybody by dx squared, what happens? What's dx squared divided by dx squared? 1. Then you have dy squared over dx squared. Well, what is that? dy dx squared, the derivative squared. Didn't we have 1 plus a derivative squared, square rooted? Remember that stuff? Yeah. All right, we're going to do the same thing today, but we're not going to divide by dx squared. We're going to divide by dt squared. Because today we have parametrically defined functions. That means x is a function of a third parameter. There's x and y, now there's a third parameter. X is a function of t, let's say time, and y is a function of, say, time, okay? All right, so this is what's going to happen. We're going to divide everybody by dt squared. Let's do it. Divide by dt squared. I'm going to solve this differential equation for L. So you get dx dt all squared. Well, what's that? What's dx dt all squared? What does that mean? Dx dt squared, the derivative, x prime, right? And then here you have y prime squared equals this thing. Okay, so let's write that down. I'm going to write it over here somewhere. All right, so I get dx dt all squared plus dy dt all squared equals dl squared over dt squared, right? Now think variable separable. I'm trying to get L alone. What are you going to get rid of next? What are you going to move around? Before I can integrate, what do you got to move up? The dt's, right? Okay, so let's do that. Let's write dl squared is basically x prime squared plus y prime squared all times dt. All of it. Now, what else can you do? I'm trying to get L alone. What else can you do to get L alone? Square root. Okay. So how about, all right, let me write that.
Wait, isn't it dt squared?
Yeah, dt squared over d, yeah, it's dx squared over, oh yeah, this part. Yeah, I'm sorry, I didn't square root yet. Oops, you're right. Okay, so let's square root. Here we go. dl is the square root of this mess. Dx over dt squared plus dy over dt squared, square rooted, and we'll square root this too. All right, now how do you get rid of the d? Integrate, right. So this is my Riemann statement. This is the length of that little piece, right? That little piece right there, which we're simulating with this little straight line segment. That's dl, okay? I want to get L. I want to add up all the little pieces. So L is the integral from t1 to t2. Remember, this is a function in time. So you start at some time and you end at some other time of this radical. Times dt. All right, there's my new arc length formula for parametrically defined paths. So let's try it. Take a look. I'm going to start really tough. Are you ready? 78. The 70s were bad. BC, 7. Are you ready? A 7. 7s have been banned. There are no more 7s. They've been banned. There's no more 7s. Have you noticed that the new exams only go up to 6? AB6, BC6? Yeah. BC 7s were monstrous. Okay? But guess what? You can do it. Are you ready? It's just this. All right, here we go. Take a look at 78 BC 7, which says x of t is given. It's e to the 8t over 4 minus 2t. And y of t is given. And that's e to the 4t. That's a 2t, yeah. Okay? Huh? Well, wait. That's what's given, part A. If that's your position, what's your velocity? So parametrics and vectors, they go hand in hand. This could be a position vector. How would you get the velocity vector? You take the derivative, right. So what's x prime of t or dx dt? What would you get? What's the derivative of this? How do you differentiate e to the u? You get e to the u times chain rule, which is 8. Right, and don't forget it's still over 4. And what's the derivative of this thing? So minus 2. Okay. So now what's y prime? Times 4. Good. All right. That was part A. Part B. Can you get the arc length of this parametrically defined path from t equals 0 to t equals 1? Okay, let's do it. Now remember what we're doing. We're just doing this formula, right? So we're going to take the derivatives that we had, square them, add them, square root them, integrate them. It sounds like a lot. It's actually doable. All right, so here we go. L is going to be, whoops, L is going to be the integral from, what did I say? 0 to 1. Of, what goes here? What's the formula say? Square root of some big mess, dt. Well, what's the big mess? It's dx dt squared. So, by the way, this is just 2, right? So 2e to the 8t minus 2 squared. What else do I have to write? Plus who? 4t all squared. Perfect. And that sounds like something impossible. First you got to square them, then you got to add them, then you got to square root them, then you got to integrate them. There's probably no closed form antiderivative for this, right? Well, wrong. It actually works out nice. That's where people got all flustered. They're like, I can't do it. And they skipped the question or something. I don't know what happened. Okay, so. Huh? They did like the part A and then they died on part B. I don't know.
But didn't you get a little points for testing?
Yeah, but there's 9 points altogether and they got nowhere near the 9 points apparently. Because it's a lot of work to make this integrable. But it's all algebra. It's not calculus. All right, let's see. What would you do to simplify this so you can integrate it? Foil it. How about we foil stuff? What's 2e to the 8t minus 2 times itself? 4e to the 8t. What?
Wait, hold up.
Yeah. Can you do it? Oh, sorry. This is wrong. 16t. 16t. Then? Well, it was 8t, wasn't it? And? Plus 4, right? Now, if you have to foil this on paper on the side, go for it. Plus, square this, what do you get? E to the 8t, right? Okay, right? When you have 2 powers in one base, you multiply the exponents, right? Okay, good. So we're integrating from 0 to 1. We're square rooting this mess with respect to t. Okay. Well, is there anything else you can simplify? Combine like terms. Who are they? The negative 8, e to the 8t, and the positive 16? Okay. Let's do that. The square root of, wow, what a mess. All right. 4e to the 16t, what would it be then? Combined? Plus 8, right? And guess what? This is factorable, and in fact, it's a perfect square factor. So can you think of, if you factor this, and both factors are the same, what they are? That's the hint. I'll give you a hint. I didn't hear you. Start again. E to the 8t, yeah. There's more. Plus stuff. Not 4. 2. That's not enough though. What's missing? What in front of the e? 2. Because you're squaring it, right? If you FOIL this out, don't you get that?
Yeah.
Okay. Now be careful. What happens when you square root a square?
It gets canceled out.
Technically, no. Not exactly. Not exactly. When you square root a square, you get an absolute value. Right? If like say you squared -3, you get 9. And you square root it, you get 3. So it's an absolute value. But does it matter? On this domain from 0 to 1, is this ever negative? So the absolute value really doesn't matter, right? So I guess I could actually drop it. But technically, be careful. Sometimes that's going to be a problem. All right, so that's really what I'm integrating. And that's not so bad, because how do you integrate this? Not yet. I didn't integrate yet. You can't plug in yet. How do you integrate this?
If you integrate e, it stays at.
Yeah, but that's if it's just e to the t. It's e to the u. So this is u sub, right? Isn't this u sub? U is 8t. Okay. So du is 8 dt. So if I replace dt, what am I going to replace it with? dt is going to be du over 8, right? All right, so this is 1 over 8 e to the u du. How do you integrate e to the u du? How do you integrate e to the u du? That's an easy one. It's just e to the u, which is e to the 8t, right? But don't forget, there was a 2 in front, and now there's an 8th. So 1/4. Right, the 8th, don't forget the 8th, don't forget the 2. All right, integrate this. Plus t, that's it, good. Now you can plug it in, can't you? No, that u sub was only for the e to the part. This is a separate integral. You can think of this as this integral plus this integral. This had nothing to do with the u sub. This part, okay? All right. So now just plug it in, right? Simple. So plug in 1, you get e to the 8 over 4 plus 2. Plug in 0, you get e to the 0 is 1 over 4 plus, well, 2 times 0 is 0. So let's see, how do you subtract 2 minus 1/4? Common denominator is 4, so that's really what? 8/4 minus 1/4 is 7/4. So isn't it 8 e to the 8 minus 7 all over 4? That's it. And guess what? I don't think anyone got that answer in 78. Oh well. All right. So that was insane, but the insane part of it was the algebra making it easy to integrate. The setup was just the formula you had to memorize. And once you got to integrating, it was just u sub. It wasn't anything fancy like partial fractions or by parts. So memorize that, right. All right, let's see if we can do a regular arc length in terms of x, not in terms of t. All right, here's a regular arc length. Ready? Well, it's only a BC4. And it's a 91. 90s weren't that bad. For some reason, the 70s were like impossible. They're not, no, they're not. They haven't been that bad.
Watch this year. Just like for physics.
Let's not talk about that. Okay, this is what you're given. Are you ready? Cap f of x, a function defined as an integral, is the integral from 1 to 2x of the square root of t squared plus t dt. This is what you're given. Now, this is not parametrically defined. The question is, though, what is the arc length of this curve, whatever it looks like, from x equals 1 to x equals 2? Now remember the regular arc length formula. Do you remember it? L equals the integral from, well, no, in terms of x. Well, they're giving you values from 1 to 2 in this case, right? But how does it go? The what? Square root of, do you remember the regular arc length formula?
dx dt squared.
No, and not in terms of t. This, no.
Yeah, what it is 2x.
Well, wait, back up.
X prime, so it's x.
dy dx, right? If I divide everybody by dx squared, right? What do you get? 1 plus dy dx squared. 1 plus the derivative squared, right? Okay, so I'm going to do that. 1 plus the derivative, that's a dy dx. We've done this. Dy dx. I can't do a y. What's going on with the y?
It's just y.
Yeah. Squared dx, okay? So if you have y as a function of x, take its derivative and integrate with respect to x, right? Well, this is y as a function of x. I need its derivative. What's f prime? That technically was part A. This is part B. Part A, what is f prime? If that's f, what's f prime? How do you take the derivative of an integral equation based on the second fundamental theorem of calculus? You know this. Take this and what?
You put it in.
Plug it in. But if it's more than just x, it's like you're plugging in a u, and when you take the derivatives of f of u, you got to do chain rule derivative of du dx, right? So what's the derivative of this? 2. So plug in that and multiply by 2. All right, so let's write that down. Cap f prime of x is the square root of, well, what is it? Plugging in 2x. What happens when you do 2x squared? You get 4x squared. Plus what? 2x. Times, don't forget, the 2. Okay, that's the derivative that we're going to use. Okay. So that was technically, that was part A. This is part B. All right, so let's see. L is going to be the integral from 1 to 2 of the square root of 1 plus that squared. Okay. Now what happens when you square this stuff? Square this stuff, what do you get? 4 times 4x squared plus 2x. Don't worry, from 1 to 2, this is not negative, so it's not an issue about absolute values or anything. And now it's in terms of x. Good. Okay, is this one doable? Let's see if we get a nice easy integral out of this. Hopefully we can. If not, you could use a numerical estimate from Hal. All right, so what would you say you could do here to simplify stuff? Distribute, okay. The integral from 1 to 2 of the square root of 1 plus, well, what is it? 16x squared plus 8x. Well, let me write it this way. Put the 1 over here, get rid of this, dx. Guess what? This is, again, a perfect square trinomial. If you factor it, both factors are equal. So this is a square of what? If you can't square root it, you're screwed, basically, is the moral of the story today. 4x plus 1. If you square this, if you FOIL it times itself, don't you get that? Okay. Now we're going from 1 to 2 and we're square rooting this. Now remember, we get the absolute value, right? But again, from 1 to 2, is this ever negative? No. So technically the absolute value doesn't matter, but let me write it just in case. Absolute value of 4x plus 1. But we can ignore it here, right? Because it's never negative. So how do you integrate that? Ignore the absolute value. Think it's parentheses. This isn't even u sub. This is even easier.
2x squared.
Yeah, it's x squared over 2 times 4 is 2x squared plus x evaluated from 1 to 2. Was that so terrible?
Yes.
Really? Okay. Plug in 2. You get 2 squared is 4 times 2 is 8 plus 2 minus plug in 1. 1 squared is 1 times 2 is 2 plus 1. So guess what you get? This is the hard part. 7. He's counting on his fingers, Steve is. See, that's a secret. That's how you get to be the pizza guy. Okay. So, so if this is the curve that we're trying to get the arc length of, from 1 to 2, the arc length is simply 7. That's astounding, but there it is. All right. No, one more. Okay, ready? Try this one on for size. Now, remember that tomorrow we're doing vectors, but it's really the same as parametrics. Next week we're doing polar, and I'm going to show you how polar is just like parametrics right now. Consider the following parametrically defined curve. What if x of theta is r times cosine theta, and r is some constant? R is like 2. Well, hang on. And y, right, instead of t, it's theta, right. And y of theta is r sine. Question A was graph this path. How do you know what the hell this looks like? For a given value, I think they said r was 2. It's a circle, right? Look, remember way back when we talked about polar mode, didn't we say that x equals r cosine theta and y equals r sine theta when we had the unit circle and all that crazy stuff, right? Let's see if we can graph this on Hal. Let's see, Hal. Get out of this. Get into parametric mode. And go to y equals. And remember, we did stuff like this the first week of school. Oy. Okay, so now they don't have theta here. They use t's, right? It's a t. The theta is just a dummy variable. Doesn't matter if you call it t. So, and they said, what if r is 2? So you could graph it. So 2 cosine. T is the variable for parametric mode. And 2 sine. T. Boom. All right, now go to the window. The window, this is affected by your zoom. This is not. But this is how you trace. You're tracing on T. Now, I usually have 0 to 2 pi in increments of pi over 24. This is pi over 24. Why? Because when you trace it on this T step, you get things like pi over 3, pi over 4, pi over 6, all the reference angles come up nice and easy, okay? So now I don't know if I need that big a zoom. I'm going to go to zoom 4. Zoom, when you zoom, it just changes the x and y stuff, okay? So I'm going to zoom 4 this. The t isn't changing. And guess what you get? A circle of radius 2 centered at the origin. Okay, good. So here's part B. Part A was graph it. Part B is, what is this entire arc length? How long is this arc length? What are they really asking for? Well, the circumference of a circle, which involves pi. Yeah, exactly. All right, so guess what? We're going to derive the circumference of a circle formula that they threw at you in PAG Honors Math Grade 1, didn't they? How do you get the circumference of any circle? Whatever. 2 pi r, right? Well, did they do an arc length to prove it? They just threw it at you. Did they do any derivatives? Did they do polar mode? Did they do parametrics? They sloughed over all kinds of stuff. Oh my God. Okay. It's PHE. All right. So anyway, so let's do the arc length. Part A was graph. Right? This is a like a vector problem. This is the position, right? Part B is graph. Part A was graph. Part B was, what are the derivatives? All right, what's x prime? Now remember, this is just a constant. The only variable is theta. So r times whatever the derivative of cosine theta is, what is it? Negative sine theta. Okay. And what's y prime, or dy d theta? What do you say? R cosine theta. Okay. So far, so good. 91 BC 4. Was this terrible so far? No. All right, now they said, give me the arc length for theta varies from 0 to 2 pi. So how do you do the arc length? The integral from 0 to 2 pi of the square root of negative r sine theta all squared. What else? Plus r cosine theta all squared d theta. This is just like the parametric equation, parametric arc length we did in terms of t. It's in terms of theta. Big difference. Alrighty. Well, that looks impossible, doesn't it? But not really. When you square this, what do you get? R squared cosine squared, right? Plus?
Can you do the identity?
Yep, that's coming up. Go you. All right, so what do you get here? Cosine squared, right. Okay. And the d theta, remember, is outside. Oh, sorry, this is sine. Whoops. Oh, yeah, that's magic. That happens every other Friday. Okay, that's right. Yeah, that's one of those trig identities we just throw at you, yeah. No. Now, what's nice about this is, look, what's nice about this? R squared is a common factor. Factor it out. And cosine squared theta plus sine squared theta plus cosine squared theta is 1. What's the square root of r squared? That's all that's left. 1 times r squared, right? Well, technically absolute value of r, but r is the radius, so it's not going to be negative, right? So it's the integral from 0 to 2 pi of r d theta. Now remember, r is just a constant, some number. So forget it for a minute. How do you integrate d theta? That's all you're integrating. Theta. So you get r times theta from 0 to 2 pi. So plug in 2 pi for, this is where people get stuck. For where? For theta, right? So it's r times 2 pi minus r times 0. Well, guess what that is? 2 pi r. You've just proven the circumference formula. Scroll down, actually. Yeah. The paper's going down. The scroll's going down. Okay, that's it. Amazing. Okay. And like that, you can do a lot of stuff in polar mode. That's technically polar mode. We'll talk about that next week some more. All right, let me just save this because that's all she wrote, okay? So done.